Saxon Algebra 2, Lesson 27. We're going to talk about rational expressions, which is a phrase that sounds really hard, doesn't it? It sounds like something complicated and frightening. Here's the thing though. Fractions, a fancy name for fractions is rational expressions. It's not exactly the same, but see how it's the ratio is in there? It's kind of like fractions. See that without the C, this says ratio 2, right? So fractions are ratios. When we write something like that, 3/4, right? That's how we usually say it. We just say 3/4. But we can also call this the ratio of 3 to 4. We can say that. We don't normally, but we can say that. And I don't think we've gotten to it yet, but there's a certain type of word problem that plays off this, this way that we can say it. So fractions are rational expressions. It's no big deal. Oh, look. I used a weird place in the book. All right, so this is lesson 27. Continuing. I skipped that because I didn't have enough room to do the problem, so that was weird. Okay, example 27.1. Add 4 over x plus 6 over x plus a. Okay, so we want to add these. We're adding fractions. Oh, we know the rules for adding fractions. In order to add fractions, the denominators have to match. So number one step is to match the booties. Right? Now, the way that we do that, we know how to do that. You find the least common multiple of the denominators, right? And then you adjust one or both fractions so that the denominators match. And then you can combine the tops and the bottom stays the same. But here is a good reminder. Write this down. The only way we can adjust our denominators is by multiplying. We cannot add or subtract. So as tempting as it is to think, well, let's just add a to this side. We'll add it to the bottom, we'll add it to the top. We can't do that. We can only multiply in order to change that. That's why I like to call, instead of the least common denominator, I like to call it the least common multiple because it says multiply right in it and it helps us remember no adding. We can't add a to this. We can only multiply. So just like we do when we have denominators that are numbers, like say 7 and 5 that don't fit into each other at all we can do is multiply these guys together. So our least common multiple is going to be x times the quantity x plus a. And that always feels a little disheartening because we think, oh, there ought to be a way, but there isn't. The plus sign screws us up. So all we can do is multiply. So that means we're going to multiply this side by the piece it doesn't have, right? We're going to do x plus a over x plus a. Right? And I'm going to put parentheses around these because they're binomials and I don't want to get messed up when I go to multiply. And then over here we've got the x plus a, so we're going to need the x. So it'll be x over x. And again, I'm going to put parentheses around that so I don't get mixed up. All right. Now we've got matching denominators. The other thing I wanted to say before I got into all of this is that if this was an equation, we could make the denominators go away. But there's no equal sign in sight. That tells us we're not going to be able to make the denominators go away. As much as I like to blow up a good denominator, we can't because it's not an equation. When we have expressions like these, this original thing, right? There's no equal sign, so we're going to have to live with the denominator and just make the best of it. So we use the third rule of algebra, which is the rule for expressions, and that rule says you can multiply a fraction by anything as long as you multiply the top and the numerator and the denominator by the same quantity. It's called the numerator-denominator same quantity rule. That's a bit of a mouthful. I prefer to call it the Hanna-Cranny rule. Top and bottom, give them the same thing and they'll be fine. Okay, so now we see that our denominator is going to match, so I'm going to skip ahead and write it all over our matching denominators. And here's the first way I would write it. I would write it 4 times the quantity x plus a, and you can see what I did was I just brought the 4 over to this side, plus 6x. Now, in some problems that would be fine. In this one it wouldn't be the end of the world if you presented that as an answer. But what I notice is, oh, if we distributed, then I would get 4x, and I could combine that with the 6x. So I can see that there would be some like terms. So I'm going to go ahead and do this. This would become 4x plus 4a, and now I'll combine these two for my final answer of 10x plus 4a over x times the quantity x plus a. Now, this illustrates a preference that John often shows. He likes to distribute the top but leave the bottom in the factored form. I'm fine with that. The main point that I want you to take away from this is that whether it's factored or unfactored, I guess this one's the factored, this is the unfactored, however you look at it. This is before the distribution, this is after. It's not right or wrong. They're both perfectly reasonable forms for presenting the answer. The only footnote I'd put on that is that sometimes if you distribute, you will be able to add like terms like we did here. So you want to make sure that you take that extra step, if at all possible. But generally speaking, that's perfectly fine. John shows his answer like this, as I think I just said. He tends to distribute in the top and then leave the bottom undistributed. It's 6 of one, half dozen of another. If you get your answer and you realize that John has got a different format for his, just check and make sure that you can adjust yours to get his, that they're the same, equivalent, and then you're fine. And on a test, like let's say that we were on a test and you gave me that, I would say check for like terms and send you back to see if that could work. All right, another one. Add. I'm doing something that I don't like to do. I wrote a floaty number. I don't like floaties. Floaties don't make any sense for numbers. I'll float a minus sign all day long. I'm fine with that. But floating numbers, no. So I want to fix that. Okay, 6 doesn't have a denominator. That means he's down for anything, right? So we have to match the denominators only by multiplying. So we check out our least common multiple. There's no way we can make these match because this one has a sum. So we have to say that our least common multiple is, I'm going to write it down here, x squared times the quantity x plus 4. Okay? We'll use the numerator, denominator, same quantity rule to adjust where we need to. I'm going to do that in a different color this time because it's going to get a little messy up in here. And I don't want to make you cry. So this first one has the x plus 4. Let's give it the x squared. And I'm putting these both in parentheses. This one doesn't have anything. Oh my goodness, so it needs both. It needs the x squared times the x plus 4, and it would be here, it's the same. And this one's got the x squared, so I just need to give it the x plus 4. Okay, that looks really messy, but hopefully you can see what I'm doing. Now, the denominators are all going to match. They should all be x squared times the quantity x plus 4. So now I'm just going to do my tops. I'm going to go ahead and distribute as we go. It's going to be kind of wild, but it will be fun. We'll have fun with it. Okay. Just checking to make sure I copied the problem correctly. Yeah, it looks good. Okay, So we're going to distribute here. This will be x to the third plus 2x squared, right? I distributed those two. Now, we're going to distribute, these two can be a single term, and we'll distribute them like so. So this will be plus 6x cubed plus, right, 6x squared times x, and then 24x squared, right, this much times the 4, plus 2x plus 8 out there on the end, okay? So I'm just distributing what we had in the numerator times whatever we adjusted with to make the denominators match. All right, that was a lot, wasn't it? Whew. Okay, now we're ready to combine like terms. I see 7x cubed. Checking the answer as we go. Yes. The x squared, I'm going to draw boxes around. There's 2 of them. So that's what? 26x squared plus 2x plus 8. And all of that is over x squared times the quantity x plus 4. Wow. Could we simplify any further? Well, in order to cancel, we would have to factor out something from all of these terms. They don't all have x's, so we can't pull out an x. And 7, 26, 2, and 8. I mean, these are all even, but 7 messes that up. This isn't going to work. There's nothing we can factor out. So my mind just kind of zips through those possibilities before I draw my box. And double checking, that's correct. I hope these problems make you feel really smart, because look at this. This is crazy what we're doing here. There's a lot of complicated things going on. And if you're even following and making some sense out of what I'm saying, you're doing great. Okay, example, this is the last example for this lesson, 27.3. Here we go. X plus 2 okay, bigger and uglier than ever before. These rational expressions look horrifying. Again, we see that we're adding / subtracting, so we need to make the denominators match. Lord have mercy, how are we going to do it? Well, what I notice is that this fits a pattern, doesn't it? This fits that trinomial pattern that we have been practicing, and maybe I can factor it. So I'm just going to throw down some binomials and kick in some x's and see, can I find 2 numbers that multiply to 3 and add to 4? Ah, hot diggity. Look, we can factor it. Okay? So I feel so much better about that, you guys. That is really great. This is wrong. There, I just copied it wrong. Okay, so this is really great. I'm gonna lightly squiggle that out so I don't let it confuse me. This is the new denominator here, and when I compare this one to this one, I feel so much better. Yes, there's addition in these, but we're multiplying them as binomials. That is a whole nother thing. So for my least common multiple, I can put together, I'm gonna choose the x and the x plus 1, and then I can multiply that by the third factor, which is x plus 3. There's adding within the binomials, but all the binomials are being multiplied. So that allows me to create a least common multiple that looks like that, which is a far better thing than having to start over with all of these. Well, we're already, never mind, that didn't make sense, but never mind. We can do it like this. Okay, now I'm gonna go through and see what each one needs. You need x over x. I'll write it down there so we can see it. And you need quantity x plus 3. Okay, I feel much better now. That turned out to be much more manageable than what we had here, right? Okay, so now this needs parentheses, so I feel better. This is just a 1, so that's really nice. I'm going to distribute this and write my answer here. The denominator we know will look like this. And again, I can write these in any order I want because they're factors in multiplication and order doesn't matter. So I can do that however I want. All right, now I'm going to distribute up here. X squared plus 2x. Now, I have to distribute, the 1 wouldn't be a problem, but I have to distribute the minus sign. So it's going to be minus x minus 3. That is kind of tricky, isn't it? So make sure that when you have a minus sign in between, you're really careful that that gets distributed. Okay, now, let's see, it looks like I just have this pair of like terms, so my final answer is going to be x squared plus x minus 3 all over this thing. X times quantity, x plus 3 times quantity, x plus 1. Double checking. Yes, that's our final answer. Yay! Okay, rational expressions do not scare us. We can't make the denominators go away, but we can do some damage and combine them into one relatively cute little fraction. That's the end of 27. Goodbye. I will see you for lesson 28.